Hey everyone, welcome back to my channel. If you're into stargazing or just curious about the universe, today's video is for you. We're diving into the world of telescopes, the different types, how they work, and some essential math that every backyard astronomer needs to know. I'm using my two trusty scopes here. This 80mm refractor with a 500mm focal length and my 130mm reflector with a 650mm focal length. We'll cover refractors, reflectors, and Cassegrain designs, but I don't own one of them as yet. Plus crunch some numbers on maximum magnification, F numbers, and maximum magnification power. We'll also be looking at the true field of view. Stick around, this is going to be eye-opening. Shall we go? Let's jump in. First up, let's talk about refractor telescopes. These are the classic ones you might picture like Galileo's original design. A refractor uses lenses to bend or refract light and focus it into an image. Light enters through the objective lens at the front, gets refracted, and then you view it through an eyepiece at the back. My 80 by 500mm refractor here is a great example. The 80 is the aperture, that's the diameter of the objective lens in millimeters, which determines how much light it gathers. The 500 is the focal length, the distance from the lens to where the light focuses. Refractors are awesome for sharp, high contrast views of planets and the moon because they don't have a central obstruction. But they can get pricey for larger sizes due to the glass needed and sometimes suffer from chromatic aberration. That's when the colors don't focus perfectly, creating a halo effect. Modern ones often use special glass to fix that. Okay, now moving on to reflector telescopes. These were invented by Newton to avoid the same color issues of the refractors. Instead of lenses, reflectors use mirrors to reflect light. Simple. Light enters the tube, hits a curved primary mirror at the bottom, bounces to a smaller secondary mirror near the top, then out to the eyepiece on the side. Check out my 130 by 650mm reflector. The 130 is the aperture, which is bigger than my refractor, so it collects a lot more light for fainter objects like galaxies. The 650 is the focal length. Reflectors are generally a lot more affordable for larger apertures and great for deep sky viewing. The downside? They need occasional collimation. That's aligning the mirrors and the secondary mirrors. We'll cover that at a later date. Sometimes secondary mirrors can create a tiny obstruction, which can slightly reduce contrast on planets, but overall, they are absolutely fantastic bang for your buck. All right, now, let's hit the Cassegrain telescopes. These are a type of reflector, but with a clever folded design. Light enters, hits the primary mirror at the back, reflects to a secondary mirror at the front, which then bounces it back through a hole in the primary to the eyepiece. This makes them compact and they have long focal lengths in short tubes, perfect for portability. Popular variants include Schmidt-Cassegrains, SCTs, and Maksutov Cassegrains, MAK. They're both versatile for planetary and deep sky observations. Sorry I haven't got a personal one to show you today, but if you're into astrophotography, these are often the go-to because of their size and stability. They can be a bit more expensive though, and like reflectors, need collimation every now and then. Okay, let's get into the scary bits, the maths. Grab yourself a little calculator, an abacus, 10 more fingers, 10 more toes. Let's have a look. First, the F number, or the focal ratio. This tells you how fast your telescope is. Lower numbers mean brighter images and wider fields, and that is great for deep sky. The higher numbers are better for planets. The formula is simple. F number equals focal length divided by aperture. So, for my refractor, which has a 500mm focal length and an 80mm aperture, it would equal 6.25. So it's an f6.25. Pretty fast and good for wide views. Let's just have a look at that math. It was the focal length 500 by the aperture 80, and we divide those, and that gave me the 6.25. Let's look at the reflector, which has a 650mm focal length and 130mm aperture. So 650 divided by 130 equals 5. So it's even faster than my Celestron, and it's excellent for faint objects. Let's dive into magnification. This will tell us how much bigger an object appears for your telescope. It's super easy to calculate. All we've got to do is divide the telescope's focal length by the eyepiece's focal length. For example, my refractor is 80 by 500. This means it's got a 500mm focal length. If I use a 10mm eyepiece, I divide 500 by 10, giving me 50 times magnification. That means Jupiter looks 50 times larger than with the naked eye. This is perfect for seeing the cloud bands on it, or moon or craters on the moon, I should say, with some detail. Just remember, too much magnification can make images dim and blurry. So 50 times is a sweet spot for clear, bright views with this setup. Sometimes I'll push it. I might put a Barlow on there, but we'll talk about that at a different time. Now let's try the same 10mm eyepiece on my 130mm by 650mm reflector. This has a focal length of 650mm. Again, divide the focal length by the eyepiece. 650 by 10 equals 65 magnification. That's a bit more power, great for zooming in on planetary details like Saturn's rings, which we can't really see at the moment because they're side on. And with this telescope, 65 times will give you beautiful, crisp views of the moon and its craters. But this telescope, you can take it all the way up to like 200 for craters of the moon, and it's amazing. And that's it for our telescope adventure. From my 80 by 500 refractor to the 130 by 650 reflector, we've covered how to pick your scope and crunch numbers like magnification to explore the stars. Now it's your turn. Get out there and observe. Tell me in the comments what you've spotted in the night sky. If you've loved this, smash that like button, subscribe, and ring the bell for more cosmic content. Thanks for watching, and here's to clear skies.